All right. Howdy, Ags. I hope your 321 semester is going well. And today we're going to go over a bit more of a complicated operational amplifier example or op amp. And it's going to involve a difference op amp and some transfer functions to make it a little bit easier. And just so that we make your life easier too, we're also going to be working a lot in the frequency domain, so you don't have to solve this monster of a circuit in time domain. The thing that's most important to do at first is to identify what op amps that we have in the circuit here. So let's take a look at the top branch first. Starting off, you can see that op amps 1 and 2 are two different types. So op amp 1 that's on the left-hand side is a inverting, and the one on the right-hand side is a non-inverting. And then op amp 3 on the bottom, that is also a inverting amplifier. Now, the two transfer functions or formulas that we'll need are for the inverting and non-inverting respectively. So for inverting operational amplifiers, it's going to be negative ZF over ZR. And so what you're going to end up doing is a little bit different for the non-inverting operational amplifier. So it's going to be 1 plus ZF over ZR. Just like that. And so you'll use these interchangeably, and those two formulas will be very important for shortening some of the mathematics so you don't have to do a ton of nodal equations. So looking at the final operational amplifier, the way that it branches and feeds into the opposing terminals means that it is a different operational amplifier, since both actually have something feeding into it and it's not just grounded. So to find our solution, we'll start by identifying the transfer function for that top branch for the V2 source to get our V out double prime that you can see in the top branch. So because the transfer function definition for the frequency domain is h of s equals V out over Vn, we can establish our relationships to be used in our final solution. So let's take a look and start building those transfer functions. So for h of s, we're going to go with negative R2 over R1 for that very first non-inverting operational amplifier, or pardon me, inverting operational amplifier. So because the positive terminal is grounded, it's just going to be negative R2 over R1. And then moving on into our next op amp, you do need to go ahead and make sure you convert the
our inductor here.
Yes, thank you, Will. Our inductor here into the S domain, which all it's going to be is LS. So that's how we've constructed our transfer function for that op amp. And because they are two op amps in series, we can actually multiply both of those transfer functions together to get one single transfer function for all of V2, just to make the math a little bit simpler.
And with a little bit of simplification here, we get this bad boy as our transfer function for that branch. Let's see, here we are.
Awesome.
Remember, don't forget to distribute that sign there, the negative across both terms here.
Precisely. Now that we've established that first relationship, we'll do the same thing on the bottom branch. So while there is only one op amp, it might look a little bit confusing at first going to that V1 branch, just because of that capacitor. But again, one of the benefits of working in the S domain is it's a lot easier to combine those different components. So first of all, we're going to convert the capacitor into S domain. So it's going to be 1 over SC. And now that we've converted it into S domain, while the ZF component might look a little bit more complicated, we can just treat them as parallel components, and that's how we can obtain our solution for this transfer function.
See here, this ZF term is going to be in reference to this bad boy, because when we say ZF, our ZF stands for feedback. So our entire feedback loop here can be combined, as Caleb said, into one parallel or one single branch that we can combine using our good old friend, our parallel equation. So we're going to multiply the top terms by each other over our terms adding up to each other. And so this was great and everything, but even if we do a little bit of simplification, no one likes having a fraction in our fraction. That is just not fun for anyone to grade or for you to do math. So we're going to simplify that by multiplying a little SC to the top and the bottom, and which gives us a final ZF of R4 over 1 plus R4SC. And so that's only one of our ingredients here, and I'll toss it back to Caleb as I continue to return us back to our transfer function here.
So fortunately for us here, we're working with an inverting operational amplifier. So for the transfer function, we don't have to do too much distribution. It's just going to be that ZF that we just found and that Will helped outline. It's going to be that all over our ZR, which in this case is just a simple resistor. So it's just that over R5. And then we can go ahead and simplify that a little bit more by putting that R5 into the denominator. And then that gives you the transfer function that relates V1 to V out prime.
But I almost made a little error here. I left off my negative sign. So even as we continue to simplify, something that will come up time and time again is, remember, it's just algebra, which includes carrying over our negative signs.
Precisely. So now that we have everything, both of our transfer functions for the top and bottom function, or top and bottom branches, we can move on to our final nodal equation. So something that's important to note is that each of the nodes of the op amp are equivalent going into the difference op amp. So we can work through it in such a way to set up our equations to be pretty simple. So Will, why don't you go ahead and start talking a little bit about how we solve the VA nodal equations?
Absolutely. So the biggest thing here is, as we're working these problems, we want to have an end destination in mind. And in this case, right, our prompt being that we want to find our V out. So that has to be in terms of things that we have that are given. And really all we have that are given are our individual components and our voltage sources. Now, we'll return to these later, but our transfer functions, which also have the definition of V out over, in this case, V1, or in this case, V out over V2, we can rearrange these into something that we can use later. However, right, these both have their own V outs that then become, or that are then fed into here. However, we know what this voltage is up to that point. We don't know it beyond this point simply because there's another voltage drop over this resistor, or in this case, a voltage drop over this resistor. So that's why we kind of have to use a little bit of nodal here. Let's see, right, so we're calling this one V prime, and we're calling 2 V double prime, so it's easy to remember later, and we will return to rearrange that. But for now, right, we have our VAs. So we want our VA to be in terms of V out prime in this instance, because that will give us a direct relationship without having to worry about our final V out that we can plug into that final equation that will be ultimately rearranged. So let's start with that. So we'll do our little standalone technique here. So we're going to look in every direction from this node. So this is going to be looking to the left. So this is our so drawn ground. And so we're going to start that off as our VA minus 0, right? Our ground is 0 over R9. And then we're going to add that up with our VA minus our V out prime, because remember, we know what it is up to that point, over R6. And then that's all we can say from that branch, because it then feeds into the op amp. But we don't necessarily know from there, which is why we have our little equivalence statement here based on our feedback loop. So with a little bit of mathematical magic, we are going to simplify this by multiplying our like term of R6, R9, which is going to give us a little bit of, let's see, our VA R6 plus VA R9 minus V out prime R9. all equal to 0. So from here, we're going to do a little bit of rearranging, which is going to just essentially, see, I already have it grouped here. We're just going to pull our VA out of this term, which is going to leave us with an R6 plus R9 VA equal to V out prime R9. And so we're just going to get this into a VA equals V out prime R9 over R6 plus R9. There it is. It is beautiful. And we will use this to plug in to our next nodal equation we will do. Using a similar method of standalone, we are going to start with our VA minus V out double prime, right? Because that's feeding in from our top branch here, because we know, again, up to this node what that voltage is, and then that's all we can say from there. From observation, we can say. And then we put that over R7, which is that resistor there between the two voltages. And then we were gonna do a little bit of add, my bad there, VA, again, minus V out over R8 equals 0. So this innocent looking equation here is going to start getting really fun. And that's mostly because we're going to have to do a little bit of rearranging as we did earlier, right, with our like terms of R7 and R8. And so, which is going to eventually give us a little bit of R8, and don't quite distribute this yet, because we're going to do a little bit of plugging and chugging, shall we say, before we fully simplify and start rearranging.
Yep.
So,
yeah. Well, you stole the words
is
right out of my
nice.
mouth. That's kind of just the overall strategy with any op amp in frequency domain. Honestly, sometimes they look really complicated, but if you can learn how to segment each op amp into smaller parts and then start combining and combining and combining, you can just plug and chug your way to the end.
And so here we have our little equation of only one of which really is a voltage source that is given, which means we need to do some plugging in here. Now, we do know VA, and we do have, or at least we can get our V out prime, and then eventually, as we established here, our V out, V out prime and our V out double prime. So let's rearrange this real quick by simply doing a little bit of V out prime equals V1, and then all essentially the same term. R5, R4, SC. Beautiful handwriting with the mouse there. And then we have a little bit of rearranging again up here. Now, you don't really, I wouldn't distribute this yet. So I would leave that on the outside, because remember, we do have two terms since this was non-inverting. So let's not complicate things until the very last minute, because when it comes to system realization, it's going to be a lot of comparing perhaps a transfer function, or at least a function that you will get, with one that may be given. And so in order to do direct comparisons, you don't really want to make the term so cohesive until the last minute, so you can kind of see what you should be trying to compare when it comes to terms and placements. All right, so here we have our beautiful term here. So we can now go ahead and plug in our VA, right? Which is going to give us a little bit of V out prime R9 R8 over R9 plus R6. So this is pretty much all the same, but we just distributed our R8, if you're wondering where that came from. And then we just have a little bit of V out double prime R8, which we will plug in after. I really wouldn't ever plug in more than one term at a time. So in this case, we're doing VA first, because usually that invites a lot of room for error. And we don't like that, especially when we start getting to all this good work and good math and good theory, only to have it stolen from us by our loose and fast grasp of algebra, our good old friend. So now that that's kind of simplified a little bit here, we're going to start going through and plugging in and simplifying our V out primes and our V out double primes so that we can isolate our V out and then get it in terms of something that our graders would recognize and be happy with. So next up here, we are going to substitute in our V out prime. And so I know I said earlier that you want to kind of be careful. I mean, we have V out prime and we have V out double prime, right? They're essentially both similar substitutions here. So we're going to leave it very, very non-simplified to begin with. So we're going to end up here with a V1 R9 over R9 plus R6. And don't forget our R8 up top. And then our term that we just brought in. So we really aren't going to want to distribute our voltages because we like to leave that kind of out front with our impedances connected to it. There we are. Beautiful. So that's our first term. And then going to move over, have our V2, R8, R2 over R1. Again, all we really did was distribute. And so we'll leave our V2 on this one as well. Why not? Because we can flex our algebra skills by just pulling that bad boy back out. Let's see, R1, R3. Moving on to our other little term here, which is going to be a V1. And then a remainder from our original equation, R9 plus R6, multiplied by our next impedance, which is from our branch of R5 plus R5, R4SC. It's beautiful. Now you're wondering where that V out went, that pesky V out. Well, we just moved that over here because we're just going to leave the R7 on it, and we're going to wait till the last minute, put a bow on it by multiplying out our 1 over R7 to this side so we can get V out on its own. So again, this is kind of what we're looking at right now before we start distributing.
Something that's
oh yeah, my bad. Go ahead,
Caleb. Looking at your transfer function before you start plugging and chugging, it just depends on what helps you with algebra. So for some people, you could just go ahead and plug your V out prime and your V out double prime in. But for some people, you might also finds that since your V out prime terms, both of them have a denominator of R9 plus R6, you could go ahead and combine them if you wanted to before you plug in V out prime. But again, it's more up to personal preference than anything else and what helps you with the algebra.
So once we do a little bit of razzle dazzle here of comparing like terms here and comparing like terms here. So all we're going to do, right, we're going to do our R9 times our R5 times R5, R4 SC. And then we're going to do a little bit of R6 times R5 plus R6 times R5, R4 SC. So that we're going to get one big like term in the end where we're going to get V1 multiplied by, and remember, we're going to distribute that negative sign out to get R9, R8, R4 minus, right? Because we're going to do the same thing over here. All that really changes is our top term here, which is how we can simplify this and combine into like terms. So then we're going to get a little bit of R9, R7, R4 over, oh, that's right, it gets messier. Don't you worry about it. R5 plus, yep, that's a 5. R5, R4, R9, SC. And then essentially the same thing, just with an R6 attached to everything here. Let's see, in our last term here, R6, R5, R4, SC. Beautiful. Okay, so our next term, right? Much easier, right? All this term is missing is an R3 down here. So we just multiply out an R3 down here to get an R3 up here as well, so that we can combine these like terms and pull our V2 out, which is going to end up giving us an R8, R2, R3. Don't forget that R3, plus R2, LS, R8 over our very elegant R1, R3. And remember, equal to V out R7. Always remember to bring this down with you. Sometimes you forget about it, get a little lost in the sauce there. And then, you know, just like that, you forget to multiply an R7 across, and then you lose 2 to 3 points on an otherwise utterly perfect answer. So this is almost what we want. Our little problem here is that this is a difference op amp. And I'm not seeing a difference here because I see an addition sign. So what we're going to want to do is just pull out our little negative sign here, swap this around, which will give us our beautiful final answer. Once we also remember to distribute our 1 over R7 over here, will give us a beautiful final answer of V out equals, remember that V out's by itself, so this is kind of our final run here, R8, R2, R3, plus R2, LS, R8, over R1, R3, R7. See, so that was a simple distribution of that R7. We are going to leave that in parentheses on the next one because I think they get the idea. And no use in rewriting R7 4 different times. R9, R8, R4 plus, remember, this is all, we pull that negative sign out of both of these terms, which is how we didn't get any kind of canceling nonsense here. Over, like I said, remember, make sure your parentheses game is on point with R7. Open parentheses, and then R9, R5, right? And it's just going to be the same term again. R9, SC, scoot over a little bit, and then plus R6, R5, plus R6, R5, R4, SC. Extend this over a little bit, give us a closed parentheses, and then a closed parentheses. So in review here of this last little step, let's see, here we are. So this is our simplified term in all its glory. This is an 8, I swear. And so this looks like a difference op amp, right? Because we have our voltage with its impedance minus our other source voltage with its impedance, which is what we are looking for. So yes, this is a general form. Kind of understanding where you should go, where you're going, kind of helps you kind of check yourself, right? Like, should it be this, right? It's a difference op amp. Is it subtracting? It is. So we can kind of be safe in our assumption that we probably did this right, unless we had some algebra stumbling somewhere along the lines. We understood what was going on here. Now, if it was maybe something different, if it was perhaps a summing op amp, then obviously you would have your voltages, their impedances, all adding together to give us our V out.
There are only 2 things you really need to know for solving a circuit like this. It's your transfer function rules and your op amp rules. If you know the 2 of those, then you can do everything else from there just using algebra. So folks, I hope this video was helpful. Give yourself a pat on the back for sticking through it with us. And until we see y'all next time, thanks and gig 'em.